something does as it approaches from the left and the right, not exactly at that value. So an example would be, we're going to come to these in a second. I'm going to show you why we've been working on them. But if I give you a graph that looks like this, I know it's hardcore. It's a line, okay? You've seen these before once or twice. So say this is 2, all right? If I ask you, you're not writing any of this down, I'm giving you a preamble to help you out. If I ask you the limit as x approaches 2, and I say that this is the graph of f of x, I don't actually care what the value is at 2. So this is going to be what you're going to have to wrap your head around. I don't care if the value at 2 is this. I don't care if the value at 2 is an asymptote. I don't care if the value at 2 is a point of discontinuity. None of that. The limit is what it's doing from the left and the right of that value. Okay? So this is a line, obviously. From the left, as I approach 2, what am I approaching? Let's say 3. Okay? So from the left, as I approach 2 from the left, I'm approaching 3 on the y. As I approach 2 from the right, I'm approaching 3 on the y, am I not? So from the left and the right, I'm approaching 3. So the limit would be 3. And you're like, yeah, cool. F of 2 is 3 as well. Awesome. Okay, not always going to be a continuous line. So what happens if they give this? We're not writing any of this down because I'm going into this today. You're just paying attention because I'm trying to get you to wrap your head around what a limit is. The whole unit. Okay, what if I give you this? Something similar. So that's actually irrational. You did this in 30-1 last semester, right? It's irrational. And what happened is you had a factor that canceled on the top and the bottom, and all you were left with is a line on the top. You did this last semester. So, say I ask you for the limit. We'll say this is 5. Doesn't really look all realistic. But say I ask you for the limit as x approaches 4, and now this one is g of x. So x approaches 4, g of x. Some people will say, well, at 4, there is no value. Cool, you're right. F of 4, and you're allowed to do this in calculus, DNE. Enjoy it. It's the only short form you get. Does not exist. F of 4 doesn't exist on this graph, right? It's an open dot. But the limit, I don't care what it is at 4. I have no concern. Do not care what it is at 4. It's what it's approaching from the left and the right. So, from the left, as I approach 4, as I approach 4 from the left, what's it approaching? 5 for the y. You see this? As I approach 4, it's approaching 5 for the y. Yes? From the right, what's it approaching? 5. So what's the limit? It's 5. It's what it's approaching from the left and the right. And it has to approach the same value. Okay, what happens if I do this? Remember, we're just trying to wrap our head around something. So now I'm going to ask you at the limit as x approaches 6, right? Because that's the x I'm looking at. Let's say this was h of x. You can label them whatever the heck I want. All right. The limit is not what the value is. The limit is what it approaches from the left and the right. Well, I'm going to ask you, what is h of 6? H of 6 on the previous one was does not exist. H of 6 does not exist on this one. What's h of 6? What's y when x is 6? I think you're all whispering it very quietly. So at 6, there's nothing here, right? But there is a coordinate here at 6. What's it at? 8. So h of 6 is 8. Cool, that's great. That has absolutely nothing to do with the limit, but h of 6 is 8. Yes? Because they can give you way more not continuous functions. In 30-1, almost all your functions were continuous. You had rationals that had a little bit of asymptotes in it, but exponentials were continuous, logs were continuous, polynomials, all of them, sinusoidal, all continuous. We do a lot more not continuous graphs in calculus. So, what is the limit though? So as I approach it from the left, as I approach 6 from the left, what's it going to? 4. As I approach 6 from the right, what's it going to? 4. So what's the limit at? 4. So the limit is actually telling you on the right and left side directly close to the value, what is it doing? Is it going to infinity? Is it going to 4? What is it doing? So if it's the same value, then the limit as x approaches 6 is 4. Okay? One last example. What if I give you this? Okay, I'm going to label this m of x. So say I give you m of 5. What is m of 5? Let's pretend that that is even with 6, even though it looks like it's higher. No, it's not that. It's 6, right? M of 5 is 6, because it's closed dot, so therefore that's what it is. That means nothing with the limit. So let's look at the limit. The limit as x approaches 5 of m of x. Okay, from the left, what's it approaching? Pretend this is even with it. It's approaching 3. From the right, it's approaching what? Are they approaching the same thing? So the limit doesn't exist. I can give right and left-handed limits. So this is what we can show. We can say the limit as x approaches 5 from the left, that's how you say left, you put it after, of m of x. What was the limit as I approached from the left? What did it approach from the left? 3. And I can say the limit as x approaches 5 from the right. From the right, what did it approach? 6. But if these two don't match, this does not exist. Okay? Now what I had you do today is I had you do these. F of x plus h minus f of x all over h. I told you ahead of time that the h needs to go away, just the single h that's on the bottom. Because what we're going to do in a little bit, not right now, tomorrow, is we're going to go the limit as h approaches 0 of f of x plus h minus f of x all over h. And if h equals 0, that means I can put a 0 in for h. If I put it in, what's it going to do? It's immediately going to be faulty. You cannot divide by 0, correct? So our goal whenever we're using this formula is going to be to get that h out of our lives. If we can get that single h off the bottom to go away, we can have more h's, other h's, that's totally fine. But if we can get that single h to cancel off, then we'll be able to plug in and just get the limit immediately. So our goal for every single time we're given this formula is to get that h to cancel somehow. That h that's there. There can be more h's on the bottom, that's fine, but that h has to get away. Because if I plug in 0, we have problems. So let's look at the first one. So I did f of x plus h off to the side. And I'm going to get negative 3 x plus h squared. So I'm just going to rewrite twice. Minus 2x plus h plus 6. Why I wrote it so squishy, I don't know. So that's going to be negative 3 x squared xh, so plus 2xh plus h squared minus 2x minus 2h plus 6. Distribute the negative 3 through. We get negative 3x squared minus 6xh minus 3h squared minus 2x minus 2h plus 6. So we can put that in. So that's going to be f of x plus h. So we get f of x plus h minus f of x all over h. Okay, biggest complaint from profs. You guys don't use equal signs. Or if you do, you don't know how to use them. Or you use a lot of arrows because you're not sure if it's an equal sign, so you arrow things. That's what profs say. And I giggle because it's 100% true. How do we know something's an equation? Something is an equation that when it's typed in front of your face, it has something on the left, something on the right, and an equal sign in the middle. Right? That something on the right might be a 0. But it's an equation because it has a left and a right side with an equal sign in between. Correct? Does this have is this an equation? Does it even have an equal sign? No. It's an expression. So every single time you go to fill into an expression, you should have equal signs running down the left-hand side. because when you plug into that value, say you plugged a 2 in for x, it would come out the same every single time. It's just a simplified, different version of itself. That's all it is. So expressions have equal signs running down the left-hand side. Equations have equal signs in where they were. You just run down the middle wherever it would be. Okay? You need to know that. There is sometimes I will mark a test and I can't even find an equal sign. Like, to be found. There is not one on the page. There should be equal signs if it's an expression. So, I fill in the f of x plus h. So I'm going to get equals, because this equals the next thing. So it equals f of x plus h, so negative 3x squared minus 6xh minus 3h squared minus 2x minus 2h plus 6. And then I have to remember to subtract all of f of x. So you have to subtract the whole thing. A lot of people will go minus and then brackets and then remember to distribute it through, or people will just distribute the minus sign through right away. So we're going to get plus 3x squared plus 2x minus 6 all over h. And then, as I told you, everything with an x without an h should cancel off. If it doesn't, you oopsied. Often you forgot to distribute the minus sign through, because we have to take out a GCF of an h. So negative 3x squared, the 2x and the minus 2x, the 6 and the minus 6. And then I can take an h out, and I'm left with negative 6x minus 3h minus 2 all over h. The h's cancel, and I'm left with negative 6x minus 3h minus 2. And then I would be able to do the limit as h approaches 0 because the h is gone. Right? The next one, putting in the x plus h isn't the difficult part of it. Right? So we're going to get square root. This x is going to become a 2x plus h minus 1 minus 2x minus 1 all over h. You can distribute the 2 through, so you would get an equal sign. Do you see how the equal signs are running down the left-hand side? You should have them. If you don't have an equal sign anywhere on your page, put some. Because this is going to equal the next thing, is going to equal the next thing, is going to equal the next thing. If I put in 2 for x and 4 for h, this step would equal this step would equal this one. You get the same answers out because they are the same. They're expressions. So here we have 2x plus 2h minus 1 minus root 2x minus 1 all over h. Now, we were really good in grade 11 at teaching you that you have to rationalize your denominator. We were also really good in grade 12 at teaching you have to rationalize your denominator. In calculus, sometimes you rationalize your numerator, sometimes you rationalize your denominator. You do what you have to get what you need. In this case, we're going to have to rationalize our numerator because we're ultimately trying to get that h to cancel off. So we have to multiply by the conjugate. So we get root 2x plus 2h minus 1, and then change the sign, that's what conjugate is, plus root 2x minus 1, and then your denominator is that again. You're multiplying it by the same thing, because when you do the top, you have to do the bottom. Now, the reason why we multiplied by conjugates was so that we rationalize something. Rationalizing something means getting rid of the radical. Getting the radical out of our lives. That's what we were trying to do. That's what we did in grade 11, and that's why we did it. The reason why is when you multiply two radicals that are the same together, you get what's underneath it. So if you do root x times root x, you get x. Right? And the reason why you multiply by the conjugate is your two middle terms cancel each other off. So that's why you don't end up with a radical. So we always multiply the conjugates, and then we keep the two that aren't conjugates separate. So we get root 2x plus 2h minus 1 times root 2x plus 2h minus 1, and the roots cancel. So I'm left with 2x plus 2h minus 1. Now the middle terms, you would get this times this negative, this times this positive. So they cancel, correct? That's the point of the multiplying by the conjugate, is so the ones with radicals go away, right? So I'm going to get root 2x, I can show you the step, it would be minus, and you'd get 2x minus 1 times 2x plus 2h minus 1. And then you get the positive of that, same version. 2x minus 1, 2x plus 2h minus 1. And then they cancel. That's the point of multiplying by the conjugate. It gets one term positive, one term middle term negative, and they go away. If you multiply by the same sign in between, it won't happen, and that's why it's not the conjugate. Then we go minus root 2x minus 1 times positive root 2x minus 1, and we get minus, and this is where the error happens, you're minusing 2x minus 1. you have to remember to minus both of those things, not just the 2x. And then it's all over. I want this h to go away. We have drilled into your head's distribution since you were little, especially in grade 10 when we started polynomials. We just distributed everything. You see brackets, you put them together. Okay? I want this h to go away, so I want to be able to cancel it off. So if I distribute the h into here, is that helpful? No. It'll be embedded in, and I'll have to GCF it back out to cancel it off. So that's not helpful, correct? So we always multiply our conjugates, and then we keep these other ones separate. So we're going to get root 2x plus 2h minus 1 plus root 2x minus 1. Now in the top, we're left with 2x plus 2h minus 1 minus 2x plus 1. And that makes me happy because the 1's are going to cancel and the x's are going to cancel, and I need them to get out of my life. Right? That's the rule. On the bottom, you have an h, and then you have root 2x plus 2h minus 1 plus root 2x minus 1. This h cancels off this one, and my answer will be 2 over, see how I have equal signs every single time because these are equal to each other? Writing down the left-hand side. 2 over root 2x plus 2h minus 1 plus root 2x minus 1. Done. And now the problem is gone because if I plug a 0 in for h, this is just going to be 2 times 0. It's going to cancel off. But it doesn't make my denominator 0, right? Which was the issue. Okay, this one. We end up with 1 over x plus h minus 4. That's f of x plus h. That's just putting in x plus h for this x. Then I have to subtract f of x. So just subtract that function. And then people often forget to divide by h because they already have ugly fractions. And they're like, I don't need more. Okay? But that h is the problem. That's our problem child. We need to get it out of our lives. Okay? We need common denominators. To make a common denominator, you have to multiply. You cannot add or subtract. It is by multiplication. A lot of you will try and make them the same by adding and subtracting. Watch yourself. You can't make them. This is a trinomial. This is a binomial. You can never make a binomial be a trinomial, and a trinomial be a binomial. So if they're ever a trinomial and a binomial, you have to multiply them by each other. That's the only way you can make a common denominator. So this one here, I'm going to multiply by x minus 4. And then this one by x plus h minus 4. So we're going to get x minus 4 in the top. And in the bottom, we're going to get x plus h minus 4 times x minus 4. We do not need to distribute our denominators. We do not need to distribute them. And you shouldn't distribute them because we need the tops cancel. And then we're going to be left with minus x plus h minus 4 over x minus 4 times x plus h minus 4 all over h. We have a common denominator, so we can put them together. So we get x minus 4, and then we have to remember to just subtract them all. Minus x minus h plus 4 all over x plus h minus 4 times x minus 4. And instead of writing divided by h to the side, what could we do? Dividing by h is the same as multiplying by reciprocal, yeah, 1 over h. The x is canceled, the 4 is canceled. Now I'm left with just a negative h. This negative h, the h cancels, but I'm still left with a negative 1 in the numerator. So does that cancel? And so I'm left with negative 1 over x plus h minus 4, x minus 4. Once again, that h isn't going to be a problem because if I plug a 0 into h, I just get x minus 4 times x minus 4, which is x minus 4 squared. Just so you know what we just reviewed again, this and the limits would be taught in one lesson in university. And then moving on Thursday. Because it's an 80-minute and an 80-minute. We only have 2 classes a week. Unless you have the 3 50-minute ones. They move really fast. Okay. So, we're here. Can I get you guys to turn back to this page, example 9? So what I did is I took the first few days here, and we have been covering all the math we need in order to be successful in calculus. So we covered that stuff because we're going to be getting limits. We covered odds and even symmetry. Remember, if you need even symmetry, you would put in f of x and f equal to f minus x, and f of x negative f of x for odd. And if it doesn't fit any of those, it's neither. We have went over piecewise functions. Remember how we talked about that, graphing piecewise functions and how we do that? We need that as well. We talked about making equations of piecewise functions. We did these, a lot of them. We did this where we talked about function notation and domain and range. All of those are all of our review topics. The last one I wanted to review was this one. Determine the intervals of increase and decrease on a graph. So what we're going to be able to do, your calculator right now is the only reason why you can find maxes and mins on anything over a quadratic. So if it was a cubic function or a sinusoidal, you could use your rules, but if it was a cubic function or a quartic or a quintic or whatever, if I asked you for a max and a min, you'd be like, give me my calculator, left bound, right bound, and it would spit out the max and min, correct? Quadratics, you learned how to complete the square to find the vertex. So quadratics you could do algebraically. Everything above that, when it came to grade 12, when anyone would say to me, do I have to find the maximum algebraically or the minimum algebraically? I would say no. You can't. You can't because you need to have calculus. So what your calculator is doing every single time is it's doing derivatives, and it's spitting out a max and a min for you. You're going to learn how to get the max and the mins without it spitting it out for you, because calculus derivatives give you that. Okay? Because the first derivative will give you where it increases and decreases. So we're going to talk about what are the intervals of increase and decrease if I give you a graph. So this is like a preamble so that we're set up for doing some calculus stuff. So I know from here to here, it is going down or up. Remember, we always read graphs from left to right, just like a book. So is this going down or up? It's not a trick question. It is going down. It is decreasing there. Do you see that? Then what is it doing from here to here? It's going up. It's increasing. Then what about how it happens from here to here? It's decreasing again. Then what happens from here to here? It's increasing. Do you see that? I'll use two different colors because I thought I had two different colors, but I didn't. So when I'm going from left to right, this one is, I picked a different color. This one is decreasing. To here it is increasing. From here to here it is decreasing. From here to here it is increasing. Correct? Now, where this change is happening here, so here, here, and here, that's where our increasing and decreasing is changing. Do you agree? That's where maxes and mins will exist. Whenever you change from an increase to a decrease, isn't that a maximum? And when you change from a decrease to an increase, isn't that just a minimum? Right? So when we talk about intervals of increase, decrease, we always use rounded brackets on our domains because where that equals to is going to be a max or a min. It's not increasing or decreasing. Like right here, this is not increasing or decreasing. That's a change in increase, decrease. That's a maximum, right? So when we do our intervals, our domain is going to use rounded brackets because we don't equal those values when we increase or decrease. This is neither increasing nor decreasing. It's a max. This is neither increasing or decreasing. It's a min. So if I want the intervals of decrease, I am going to say from negative infinity, because this graph keeps going. It would just keep going because it hits the edge. So I could go from negative infinity to negative 2. And I use round brackets for intervals of increase, decrease. Where's the other place it's decreasing from? And remember, it's domain, the x values. Where's the other blue from? 0 to 0 to 2. And we put that union symbol in between because that means or. Then we want intervals of increase. Where is it increasing from? The first one? -2 to 0. I thought you switched to black in there. And then the other one? 2 to infinity. Okay, don't say I'm not kind. I will give you 30 minutes to work on this instead of assigning it. Go.